My name is Adekombi Daniel, the physics teacher for STTR, that's ST&T Regency College. And here we are having physics project defense for our year 11 students. So we'll be starting, there are 12 of them. So the first person here we're starting with is Ebuka.
My name is Ebuka Izuke, who is science student of year 11, ST&T Regency College. And I'm here to defend my project, which is on equilibrium of forces. Now, the body is in equilibrium when it is at rest or there is no net force acting on it in any direction. A body can be said to be in equilibrium when it is not moving at all, or it's moving in a straight line in uniform accelerated motion. Or a body is not rotating or rotating at angular velocity. Now, there is something called moment. Moment can be defined as the point C of an axis which is proportional to the force or the distance to the opposite axis. The formula for moment is force and the perpendicular distance.
Can make use of the marker eventually.
Okay, thank you.
You have 2 more minutes left.
Now, when there is a force acting on an object, the force that is opposing in direction and magnitude and still has the same effect is known as the resultant force. The resultant force can have the same effect in an opposite direction when the force is being acted on an object in a different direction. So that is so this has the same magnitude, and this force has the same magnitude, but it's acting on this object in a different direction. It still has the same effect as F1 and F2. So F1 and F2 are equal to F2. We go to the equilibrants. The equilibrants of an object
Get ready to stop.
The equilibrant of an object is therefore the force acting.
Thank you, Master Ebuka. The time is up. You can leave the board. Now, hello. Listen. Take a question.
What is the definition of the equilibrium?
Equilibrium.
Yeah.
Equilibrium. An object can be said to be in equilibrium when there is no net force acting on it or it is at rest.
When there is no
Net force acting on it.
And so what's now equilibrium?
The equilibrium.
Equilibrium is from the word equal. Like it talks about the anti-clockwise and anti-cyclic. If I use a seesaw as an example,
So
what is saying, what you are saying, as in you are saying something else, I don't know.
oh, okay.
Yeah, you did not read, you didn't study at all.
Okay, thank you, Master Ebuka. You can take your seats.
Thank you.
Next person on the list is Miss Nefemi Omoya Jobo. So your time starts now.
We know something.
Yeah, fifth, raise the board.
So, my name is Nifemi Omoyanju and I am a science student of year 11.
Okay, can you come again?
My name is Nifemi Omoyanju and I am a science student of year 11. I'm here to talk about electric charges. Electric charge is a physical component of matter that allows it to experience a force when it is put in an electromagnetic field. It can also be known as the loss or gain of electrons. Electric charge is measured in coulombs, and 6 quintillion 250 quadrillion electrons is equal to 1 coulomb. Electric charge is a scalar quantity and can either be positive or negative. Then we have types of charges: positive charge, positive and negative charge. So basically, if it is both positive and positive, it will repel. And also, if it's negative and negative, it will repel. But if it is positive and negative, it will attract. That is the law used in the interaction of charges. Then we go to production of charges. By friction is when two objects that have equal and opposite charges collide with each other. So basically, then we have gold leaf electroscope. A gold leaf electroscope is an instrument used to detect and test for types of charge. Used to detect charges and test for the types of charge. So this is the drawing of the gold leaf electroscope, basically. This is insulating base. This is the gold leaf. This is the metal rod extension. This is the metal case. This is basically earth. This is insulating pencil. This is brass disc. So when then we have uses of gold leaf electroscope. Gold leaf electroscope is used for for the type of charge, the magnitude of the charge, the presence of the charge, and to distinguish between conductors and insulators. Conductors are materials that allow electrons to pass through them easily, while insulators are materials that do not allow electrons to pass through them easily. Examples of conductors are damp air and human body. That is why when a metal is supported by a conductor, the electrons from the metal flow through the entire human body. Then we have, if we skip to thunder and lightning conductors. Basically, a lightning conductor is a thin, pointy, and copper rod with spikes. So this is what happens basically. This is the lightning that is coming from the metal into the lightning from the cloud, wherever. And this is the negatively charged cloud. This is the charged thundercloud at the pole. So then this is the positive charge of the lightning conductor, and this is the building. So even if the lightning conductor is not able to catch the charge goes from the lightning conductor down to the earth harmlessly without any harm caused to the building as a whole. That's why lightning conductors are there to stop buildings and tall trees from getting caught by fire. Thank you. Okay.
Please, can you tell us how we can use a gold leaf electroscope to differentiate between a conductor and insulator?
When a conductor is put on a gold leaf electroscope, it's placed
Close to the cap.
close to the brass disc
cap.
a gold leaf electroscope. I don't know it. I don't know it. I cannot even remember it.
Is it not in your body?
Yes, that's on me. I don't know.
There is it. Okay, thank you.
Thank you.
All right, yeah, hello. In the course of the presentation, I'll try something.
Okay, sir.
When the presentation is, I think whatever you say in physics or chemistry is natural truth. Natural truth in the sense that it can be changed. Reaction of this and that can be changed. It is forever. I hope you understand something right now.
Yes,
So you were doing your presentation and I heard you saying did not instead of do not. Did not simply means you're referring to something that happened in the past. But right now, this thing can be repeated and the reaction will not change. I hope you something right now. So for the benefit of those that are yet to do their presentation, you're doing it. If you're talking about an experiment that was performed in that instance, then you can use did not because you perform an experiment. Is that clear? We're talking about natural truth, something that is just there. It can never be changed. Just like if I say the sun sets, the sun rose every day. The sun rose every day. Is that wrong? Yeah, it's a natural thing. I would rather say the sun rises every day. Is that clear right now?
Yes, sir.
And also, I want to say that it's the highest level of insolence and impunity for you to say whatever in the course of a presentation. It is wrong. You're on air. Remember, you're on air. And there's something I love about ST Regency College for the purpose of those that are watching us work from wherever it is. We are breathing universal soldiers. That's what we do here.
Yes.
Soldiers that can represent the school anywhere they go to, anywhere they find themselves. And one of the things that we always do, we always try to impute into our students is manners and courtesy. You know that.
Yes, sir.
So I felt so perturbed when you use whatever. Why did you use that? It was wrong. Okay? You don't act on impulse. Whatever it is, you be yourself. You calm down and be yourself. Okay? Apart from that, I think you did a good job.
Right, yeah.
You tried. Can you please appreciate that?
Please,
Next person.
the next person here is Onyedamola Onobrapeya. Please kindly write your topic on the board.
So, my name is Oyindamola Onobrapeya. I'm here to talk to you guys about momentum. So, momentum can be defined as mass motion, and every object, every body has mass. So, if a body or an object is moving, it has momentum. For linear momentum,
Sorry, when you come, you're supposed to greet first. That's the first that you're supposed to do. You can't just come out and introduce yourself on the thing.
So my name is Oyindamola Onobrapeya, and I'm here to talk to you guys about linear momentum. Momentum is defined as mass in motion. The definition of linear momentum, P, can be given as the product of mass and velocity of a body. It is a vector, meaning it has magnitude and direction. The direction, it goes in the direction of the velocity. It can be measured in Newton second. Impulse. Impulse is the product of force on a body and in the time in which it acts. It is a vector, meaning direction is also considered, and it goes in the direction of the force. It is measured in Newton seconds. Laws of motion. Motion is caused by unbalanced forces. The first law of motion, also called law of inertia, states that a body will continue to remain in a state of rest of uniform linear motion, except acted upon by external force. Inertia is defined as tendency of a body to remain in a state of rest of uniform linear motion in the absence of applied force. The second law says that the rate of change of momentum is proportional to the applied force, and it takes place in the force in which it's applied. So, The second law gives a measure to force as the product of mass and acceleration. The third law states that every action has an equal and opposite reaction, meaning force A equals to minus force B. So as I stand on this stand or podium, as the force I put a force on it, and it also puts a force on me. Fa is the action force, and Fb the reaction force. So conservation of linear momentum. This basically states that when some more bodies collide in a closed system, total momentum before collision equals to total momentum after collision. What does a closed system mean? A closed system is a system where there are no external forces acting upon except the forces caused by the collisions. Okay. Now we go to collision. There are two types of collision: elastic and inelastic. In elastic collision, the momentum and the kinetic energy are preserved, and two formulas can be written from that. This from preservation of momentum, from preservation of kinetic energy. is a tennis ball that after many bounces comes back to its original height. Inelastic collision. So the kinetic energy decreases, meaning that only momentum is preserved in an inelastic collision, and the bodies, when inelastic, when the two bodies collide, they move as one unit. So that final velocity becomes, since only momentum is preserved. Okay. So that means that kinetic energy before collision, for a perfectly inelastic collision, the kinetic energy before collision should be greater than the kinetic energy after collision. And then there's initial mass. This is the representation of the resistance to any force.
Thank you.
Mention of the name of the scientist that proposed the law of motion. What's the name of the scientist?
Newton.
Yeah. It's better Newton first law of motion, Newton second law of motion, then Newton third of law of motion. That's how it's supposed to. Thank you.
All right, you did a very good job, but I must be sincere with you. I'm not too happy with the pronunciation of some of the words, especially the motion and momentum, not momentum, momentum. I will be telling you that when you have U in the word, SUM will not be pronounced as son.
Oyekon.
First, what's motion? Motion, this is change in position in respect to time. And we are also going to talk about kinetics. Kinetics, this is the way objects move without like understanding the force, like without the force. And what are dynamics? Dynamics are dynamics. Yeah, dynamics. This is the movement of an object. So this is the movement of an object without the force surrounding it. Now we are going to move types of motion. Types of motion. First of all, we have translational motion. Translational motion, this is the type of motion in which it goes in a line without rotating. So it keeps going, it moves. And another example of translational motion is a car moving in a straight line without from one spot to another. A car. That's another example of translation. We move to oscillation. Pendulum from left to right. It's a good example of oscillation motion because it takes a back and forth movement. It's just very short. It takes a back and forth movement. Moving forward and back. Moving forward and back. Yeah, we go to rotational motion and circular motion. People usually confuse rotational motion and circular motion to be the same thing, but they are not. There is a very little difference between rotational motion and circular motion. Rotational motion is when a body, an object, moves in, like spinning around, spins around, when it keeps spinning. While rotational motion, an example of rotational motion is Earth around the sun, the way the Earth moves around the sun. The Earth is in a rotational circular motion. Earth is in a circular motion.
while a spinning disk, for example, the surface can be yours. While this is in circular motion, while the Earth, now this thing went round, is in circular motion. Yes. Now we move to Newton's laws of motion. We can't talk about motion without stating the genius of Sir Isaac Newton. The first Newton's first law of motion. Please be audible. Yes, sir. Newton's first law of motion states that an object will continue in a straight line or will stay at rest unless an external force is acting upon that object. So it says if a car is moving in a straight line, unless the car hits something, or turns, the car will continue in a straight line until an object, maybe it bumps the road. Newton's second law of motion. Yes. Newton's second law of motion states that. Let me just go straight to the third law of motion states that for every action there's an equal and opposite reaction, which means that if, like on the fire rifle, the recoil, the bullet goes this way, this is an action, then the opposite reaction is the recoil of the gun. Yes, and the opposite reaction, while the gun itself is force. Reaction. Thank you very much.
Thank you, Mr. Olalua. You come. Okay.
Any questions?
Over to the judges.
First, what have you just done? What have you just done?
I spoke about the question.
No, what is the name of what you have just done now?
Explanation.
Presentation. Is that not? It's doing the presentation. And in doing a presentation, you expected to educate us, right? Right? And if you really meant to educate us, you expected to be audible. It was more like that you were talking to yourself.
I was trying to.
No. Be audible. Let everybody hear you. Do you understand what I'm saying now? It looked like you're fidgeting in the course of the presentation. Okay? Which was very wrong. You just have to be audible. Exactly right now. And it's so common with your Gen Z generation, as you've told me. You guys like using so. It's so common. Okay? The conjunction so. It's so common. When you use so is used in a complex sentence. I hope you understand. But an instance where you guys use, when you wanted to introduce yourself, the first thing you said was so. Where is the so coming from? The so you used was not connected with a pre-sentence. You just came in and you just used so. It is wrong. Do you understand? You guys should do a work with that use of so. And of course, any presentation is formal. Any presentation is formal. So a word here is not permitted. Here. It's not permitted. I hope you understand, because you're not talking to your friends at home. This is a formal setting. Okay? And we should all be trying to use formal words. Exactly right now. So that is it. Apart from that.
Okay.
I have
Okay.
a question. When a car is moving on the level road, a car moving on the level road, what are the forces acting on it?
What are the forces?
acting on a horizontal motion? Yes.
Oh, before first acting on it is translation motion. Actually, undergo the translation motion, but the first acting, that is
Okay, but you wrote the forces meaning. Yes. You said one is the frictional force, the normal reaction, and the weight of the car. So it shows that you are not grounded in what you want to come into place.
Sure. That was probably addition.
It's still part of what you are teaching. You are just teaching us motion, right? And you taught us, you showed us different examples of motion. You even showed us an observational motion, isn't it? Good. So you should be able to tell us the forces acting on the car moving the level. It's part of what we are teaching. It's concept of motion. Okay, so I've told you the answer.
Okay. Thank you so much, ma. Thank you, Master Ola. The next person on our list, Master Faith.
Good morning, panel of judges, fellow classmates, and everyone else. My name is Faith Akinwande, and I will be presenting my physics project on heat, temperature, and expansibility. So first, we start with heat. So heat can be defined as the total kinetic energy of a body. So I'll explain it this way. This is the kinetic molecular theory. Every element or this an object, every object has molecules, and the molecules are in a state of randomness. So when the molecules move faster and faster, their kinetic energy is increased. So now the calculation of the total kinetic energy of that body is heat. So it is the unit of heat is joules. And the instrument used to measure it is a calorimeter. So next up, we have the effects of heat. So the effects of heat on the body are namely there is a rise in temperature, there's an increase in volume, it brings about chemical change, and it brings about physical change. So to explain it, increase in temperature. When the total kinetic energy of the body is increased, the average kinetic energy, which is temperature, is also increased. A change in physical state. Let's say you have an ice block. If you increase the temperature, it slowly melts into ice. For chemical change, increase in temperature can lead to changes like loss of electromagnetic abilities and some other things. So I've already explained the kinetic molecular theory, but I'll list it again. Every substance contains molecules which are in a constant state of random motion. Number two, number three. Okay, I can skip it. So heat transfer. So under heat transfer, we have three methods of heat transfer: conduction, convection, and radiation. So conduction, in physics terms, it is the transfer of heat where the average position of the molecules of the substance not changing. They vibrate but they don't move. But in simple terms, it is the transfer of heat through contact with the body. Under conduction, I have some examples here, which in your house, when you are cooking, the fire that touches the pot, and then you have food inside the pot. From the heat of the pot, the food inside gets heated up. That is conduction. And some other things like a stone floor compared to a rock floor. Next up is convection. This is the transfer of heat through fluids. So fluids contain liquids and gases. So when liquids are in a pot, for example, there are some things called convection currents. when warm moves up, cold goes down, and then it continues to circle around until there's an equal flow. Then we have some, I've already given an example. So the most important one here is land and sea breeze. When land and sea breeze, in the day, the sun is out, so the air moving about land gets hot because land is a good absorber of heat and a good radiator. So the air on land is warmer, and then but the air on sea is cooler. So the warm air moves up and the cold air from the sea comes down. That is what you call sea breeze. Then during the night, the water retains more heat, so like the air moves from the water up, then the breeze, cold breeze from the ground moves down into the water. That's land breeze. Next up, we have radiation. Radiation is the process by which heat is transferred without there needing to be an intervening medium. So radiation, I cannot skip everything. It says some things that can be used to detect radiation are radiometers, thermopoles, and electric cube. I would have drawn it, but I can't enough time. There's a lot of things to explain. Next up is the thermostat. The thermostat is a combination of all the types of heat transfer. So it has silvered walls which stop heat transfer by radiation. It has a vacuum which also stops it by conduction. Vacuum between the glass inside the casing of the bottle. It stops it by conduction and convection. Then we have insulating supports that hold up the glass that is inside your bottle. This stops heat transfer by conduction. Then we have the insulated cover, which stops heat transfer by convection, because if your bottle has hot water in it, it will be lost to push steam, which will come out of your bottle. But the cover prevents that. Then next up, temperature. So temperature is...
Thank you, Master.
No! Expansivity. Okay, expansivity. Thermal expansivity. It contains solid and liquid. So a solid, how many? 10. Okay, there's linear area and volume. Linear area and volume. So linear is this, and while the cube area is 2 of this, which equals to this. Then we have 3, which equals to QB. Here, changing linear expansivity is the change in length per unit length per degree rise in temperature, which also the same thing now for all the rest, but like it changes. Like instead of using length, it will be area, but it's the same definition. So then we have expansion in liquid. There is real expansion in liquid, which is that of the
Thank you, Master Faith. Over to the judges.
Well, I want to commend you. I see that you are grounded in what you think you explain. Even when we try to stop you, you still want to keep talking. It's very, very commendable. And I want to ask you one simple question. There are 3 examples of thermal expansion. What are they?
Linear, area, and volume, or you can say superficial or cubical for area and volume.
Okay. Thank you.
Yeah. Hey.
Hello.
I'm going to be sincere with you. You had a lot of content in your backpack.
Yes.
And it's so unfortunate that the time was not really a friend. It allowed you to talk and talk and talk and talk. I know that you have a lot of things to say, but it's all good. Okay, I'm gonna say thank you. Thanks a lot.
Thank you so much.
Okay.
Yeah.
Next person.
Okay. To say.
Okay.
You've done very well, but could you just explain diffusion? Diffusion using heat transfer.
I can't really explain it.
For example, I slept while cooking and I got my food burnt, so I have smoke.
Okay.
How do I diffuse the dense atmosphere?
Or you open your door and then because there will be air coming into the room where you burnt it, that will be convection. So the air that smoke starts to come out because warm air, which is smoke, is up and then it starts to move out. Then the cold air from outside will come in and fill in the room and all the smoke will have left your outside.
Okay. Very good.
Okay, next person.
Please, as a way of encouraging one another, once the presenter is going to stand to appreciate him. Okay? Okay.
Okay, next person here. We have Master Chinedu. I'm okay. Where is the fast?
Good day, panel of judges, faculty and people. My name is Honorary Chinedu, and I'm here to defend my project. I'm from ST and College. I'm in year 11, and my teacher is Daniel, Mr. Daniel Adekawuji. My topic today will be projectiles. So firstly, what is projectiles? What is projectile? Projectile is mainly an object that is thrown into space and is moving on its own free flow with only gravity and air resistance. And gravity is the main force acting on any objects thrown into air. It doesn't necessarily mean that there are no other objects acting on that object. There are no other forces acting on the object. Gravity is the main force acting on the object. Then next we move to along projectile motion, there are two simultaneous independent rectilinear motions. They are from along the x axis and along the y axis. Next we have concept of projectile. Let us consider a boy who releases a piece of stone from his catapult against the bird on the tree branch. The stone will travel the parabolic path towards the bird. Likewise, if we throw a tennis ball against the ball, the path of the ball towards the wall is a parabola. On hitting the wall, the ball returns to the ground and also along the parabolic path. The same type of curve is seen when the ball is projected horizontally from the top of the building. The stone or ball being projected is known as projectile. So we have examples of projectile motion. The first example of projectile motion is a flown rubber. A thrown rubber that is thrown to the wall and is bouncing off the wall is also a type of projectile motion. So because of time, I'm going to skip that.
Yes, go to the calculation area.
And move to the main calculation areas. So one of the main calculations in projectile motion is sine taking so the time taken to reach maximum height is the highest. The time taken to reach maximum height is the highest vertical distance attained as a measure from the horizontal projection plane. And the formula for it is equal to mu sine theta over g. This is the formula for time taken to reach maximum height. It is, you can derive it from We have u is equal to u sin theta. So from the equations of motion, we have v is equal to u plus or minus 2g s 2gt. Sorry. So from here we have v is equal to u sin theta minus 2gt.
Thank you, Master Chinedu. Stay there, can you?
I would love to pose a question to you. Did you take your time to peruse the topic that was given to you before you mounted the podium? Did you do it? This is what you do, right? Huh? Because I saw that you were reading outrightly from your laptop. You are reading outrightly. You're not really presenting. I'm sorry. That's just the basic fact. We want to face the brass track here. I'm going to be sincere with you. You were just reading out from your laptop without you doing the presentation. I don't know about the other judges, but that's what I saw. All right.
Why don't you have this? You know you have lost some marks for not having this. Some difficulties. Because you don't have this, I have many questions to ask you. Okay, the first question is.
Why do I ask questions? Do you have a question?
Yes, I have a question. What's the definition for time of flight in the
Time of flight is the total time taken for an object to reach. Time of flight is the total time taken. Time of flight is ultimately 2 times the time taken to reach the maximum height. So when you have, since you go to the formula for your time to reach maximum height, you multiply it by 2 to get your amount. I'm not exactly sure how to.
See, when you want to make a presentation, you need to be grounded. You need to be grounded. The most simplest part of the projectile is the time of flight. That's how simple it is, the time of flight. You should be able to define it and express it in terms of the formula. Now, even the formula, you are still, you are not even sure. What's the formula for calculating time of flight? What does the U represent?
Initial velocity.
Okay.
Yeah, you really impressed my learned grammarian here. Your phonetics actually swept me off my feet. Thank you. But I want you to help me out. I had difficulties in calculating this. Now put it down. The range of a projectile is twice. No, just put R is twice the height, 2h. Okay, all other terms defined. Find all other terms well defined, that is initial velocity. Find the angle of projection.
First thing we have the formula for the horizontal range,
Yes.
which is R equal to U squared.
Okay.
Then
It's twice the
we
height.
have the R is twice the height. So we put this in here as
What's your age?
same.
All right, thank you.
Thank you. Next person, Master Tiwa.
judges and my fellow learners. My name is Ayo Jolua Motiwa and I'm going to be talking on the topic machines. First of all, I would like to define a machine. A machine is any device or tool that allows a force known as effort acting as a direction to overcome a resisting force known as load at another point. So a machine is any device used to make work simpler and faster. There are different terminologies in machines. Mechanical advantage. It is also known as force ratio. The mechanical advantage of a body is the load over the effort. And the reason it is called force ratio is because it is the ratio of two forces, load and effort. And load is also known as output force. And effort is known as input force. So you can see mechanical advantage is output force all over input force. Then we move on to velocity ratio. Velocity ratio is the ratio of the distance moved by the effort all over the distance moved by the load. And the velocity ratio is affected by the geometry of the object. All mechanical advantage is affected by the friction. So we move on to efficiency. The form of efficiency is useful work done by the body, useful work acting on it. So work is one of the work is force times distance, and since load and effort are both forces, you can say efficiency is load times the distance moved by load all over the distance moved by.
Please amplify the voice.
Effort. And you can break it down to say the efficiency is equal to times 100. Efficiency is equal to N A all over E R times 100. Yes. So types of machines. There are different types of simple machines. I'll be starting with lever. The lever is the most common simple machine. They're made up of a strong rod that is pivoted. This is the pivot, this is the rod. Then an effort is applied here on a load that is here. So the effort will help move the load, which is usually greater. Then the effort required to move the load will be less since it is placed on this. There are two types of lever: first order, second order, and third order. The first order, the fulcrum is placed between the effort and the load. An example is scissors. If you have your fulcrum and your load, let's say you're trying to break something. This is the fulcrum, this is the effort, this is the load. Another example, for second class lever, you have an example is that a plier. You have this very not tracker. Your load is here, your effort is here, and this is your fulcrum, this is your load, this is your effort. When you apply effort here to break the knot in the center. That is the application of the second type of lever. And third class of lever, we have an example is a tongue, your fulcrum, your effort, and your load.
Okay, thank you, Master Tiwa.
Let me just explain inclined plane. An inclined plane is a rigid plane that is inclined at an angle to the horizontal. This is theta, this is your load, this is A, this is your load, and the effort is moving here, is acting in the direction OB. And your load is acting in the direction of BA.
Okay, that's okay. Thank you. Well, to the judges.
What's your name?
I will do long as you are.
Who thought you are Seriously? When you were talking and the way you were when you are explaining, you know, there's this charisma of, I don't know, trying to tell us that you know what you are doing. It's not when you are too slow and for me, I wasn't feeling you. Although you know what you are doing, but I wasn't feeling you, seriously. You need to get the audience attention. The attention wasn't there. It was a boiling class. And then you need to, when you're explaining things, try to explain it practical. It's not drawing. Try to explain it, things around you. You understand? So that it can be part of what drives your attention. Then the last part, when you were showing us an inclined plane, you said the load is in the direction of AB.
No, OB. This is the origin. The load moves in the direction of so the load is the direction of ABS because the load is taking up on the related surface.
Okay, I thought you were saying that it's facing that side. It's like it is moving up.
Yes.
Okay, thank you so
Yes,
much.
sir.
Okay.
You are giving us machines. You just gave us the abstract view, the mathematical aspect of it. I want to have a live aspect. That is examples of inclined plane.
Something like this, but
That's a wedge.
that's a wedge, yes, but it's 90 degrees. A wedge is made of two inclined planes. So half of this will be an inclined plane.
Okay, how about I'm trying to look at this. When you go to the amusement park, you see children climbing a ladder, and then they will sit on the smooth surface and they will slide down. What do we call that?
That's an inclined plane.
Okay, something like that. I want an example like that. Do you have other examples to us?
A wedge. This is a wedge. The wedge is used to split two objects, like an object. If
Okay.
your force here, the force will transfer.
Where I'm driving at is that you give us the importance of all these things. For example, if you look at our roofing models, we have different types of roofing, right?
Yeah.
Okay. We have the higher the gable. You know what's called gable? How many of us take TD here? Okay. Gable talks about the angular difference between the roof and then the top of the roof. Okay. Now, when the gable is high, when it's much, it's more costlier, but it gives that house more beauty and then air. There's so much ventilation for that building. So that's part of the aspects that I wanted you to. But good job.
Okay, thank you very much.
There's something I want to say that I observed. And Tiwa, it takes somebody that's well acquainted with you, that's well acquainted with you, to know that you do have a lot of content, but the problem is how to present it. Just like she has rightly said, add some life to it. Do you understand what I'm saying right now? And like she has said, look for something around you to check your ideas. Do you understand what I'm saying right now? So that's just what I want to say. Apart from that,
equation of motion. So, equation of motion can be defined as a derived traveling at a straight line, uniform acceleration. So the first law of motion continue. First law of motion is equals to A equals to change in velocity over time. That is A equals B minus C over T. Then you cross multiply and it will give you B equals U plus U plus A. And then the second law of motion is equal to is distance. That is distance is equals distance equals average times speed times time. That is
Thank you, Master Okekaito. Any comment from the judges?
Yes, let's just go straight to the point. I see that you actually prepared very well. Why do we have loss of motion? Okay, why do we have equations of motion?
we have equations of motion because they are used to find the straight line and they are used to find the equation of motion in the straight line.
So, what's the difference between loss of motion and equations of motion? There is no difference. Thank you.
Thank you. Next person on our list, Master Morayo Taiwo. Time starts now.
Facilitators of my fellow learners, good morning. My name is Tawo Muraya Oluwa, and I am here to talk about simple harmonic motion. Firstly, what is simple harmonic motion? Simple harmonic motion can be defined as a special type of periodic motion where the restoring force is directly proportional to the displacement from the equilibrium position and the force acts in the opposite direction. There are a few key characteristics that should be looked upon when discussing simple harmonic motion. These are, number one, the restoring force. The restoring force is the force that aims to bring the object back to its equilibrium position. Number two, periodic motion. Periodic motion is the motion that occurs in simple harmonic motion, and it is predictable and follows a regular pattern. 3 amplitude, 4 frequency, and 5 period. This will be explained later when I am talking about the calculation aspect. There are a few factors that influence simple harmonic motion. This is number one, the mass. In a mass spring system, the mass of the object influences the period of simple harmonic motion. A heavier mass would mean a longer period. Number two, the spring constant. The stiffness of the spring, characterized by K, affects the period. A stiffer spring results in a shorter period. Number three is the amplitude. Changing the amplitude alters the extent of the oscillation, but not the period. Hooke's law can be looked upon to describe the restoring force in simple harmonic motion. This law states that the force exerted by a spring is proportional to the distance it is stretched. Mathematically, that is F is equal to minus Kx, where F is the force in Newton, K is the spring constant in Newton per meter, and X is the displacement from the equilibrium position in meter. The minus sign in Hooke's law indicates that the force is always directed towards the equilibrium position. The equation for simple harmonic motion can be derived using Newton's second law of motion, which states that the force acting on an object is equal to the mass of the object multiplied by acceleration. That is, F is equal to mass times acceleration. The acceleration of the object in simple harmonic motion is directly proportional to the displacement from the equilibrium position and acts in opposite direction. Mathematically, that is A is equal to omega square x, where A is the acceleration in meters per second square. Omega is the angular frequency in radians per second. The angular frequency is related to frequency F and period T. If of the motion by the following equation, omega is equal to 2 pi F and T is equal to 2 pi over omega, where F is the frequency in hertz and T is the period in seconds. The frequency is the number of oscillations completed in 1 second, and the period is the time taken to complete one oscillation, and they are inversely related. The general equation for simple harmonic motion can be written as A is equal to, X is equal to A cos omega T plus theta, where A is the amplitude in meters, X is the displacement from the equilibrium position, T is the time in seconds, theta is the phase angle in radians. The amplitude is the maximum displacement from the equilibrium position, and the phase angle determines the initial position of the object in the center of motion. There are some real-life applications that can be looked upon when talking about simple harmonic motion. This is the number one, musical instruments. Simple harmonic motion can be used in musical instruments, in instruments such as the string instruments. When they are plucked, it produces a sound. The vibrations of the spring are simple harmonic motion, and the frequency of the oscillations determine the pitch of the sound. Number two, engineering. Engineers have to take simple harmonic motion into factor, because if their buildings or infrastructure cannot handle simple harmonic motion, that means that infrastructure will crumble and may collapse, which will cause massive death and injuries. In conclusion, simple harmonic motion is a fundamental concept with far-reaching application. Understanding the mathematics and physics behind simple harmonic motion is crucial for various fields, far-reaching from timekeeping to seismology to engineering and even our music that we enjoy. This is why simple harmonic motion is a cornerstone of classical mechanics and wave theory. Thank you.
Yes, thank you very much, Master Burayo. Over to the judges.
Okay. Good presentation. Yeah, you said, what was the topic again?
Simple harmonic motion.
It's on the board. Okay, thank you. Okay, as a simple harmonic motion, anything to do with equilibrium?
Yes.
Is the Earth observing harmonic motion?
The Earth usually. I think it should, because the Earth will rotate.
It should, or it is?
It is, because the Earth will rotate at periodic motion. That means it will be constant. And the Earth will always move back to its equilibrium position.
Okay, so then, bringing it to geography, if I may, how can we reorder our environmental imbalances using simple harmonic motion?
Wait, can you
Yes, you said that the Earth observes simple harmonic motion, that it will bring itself back to equilibrium.
Yes.
Okay, now we're having environmental imbalances.
Like earthquakes.
Called global warming. Yes. How can we reorder global warming?
Global warming.
Yes, sir. Is it possible to bring the Earth back to its balance, to its equilibrium?
No, I don't think so. I'm not sure. But there should be a way, but I'm not sure how to do
Since the Earth brings itself back.
That's when it's rotating.
That's when it's rotating.
Yes.
Definitely there should be forces that will bring the Earth back to its balance. Else, we are delving towards if we do not reorder it. Now, what's the cause of global warming?
Cause?
Yes.
Like effects.
No, what causes global warming?
The depletion of the ozone layer.
The depletion. So how do we reorder it? That is bring
the planting of more trees will be able to bring the Earth back to equilibrium. There's also the reduction of our carbon footprint. That's such as petrol and the like. That's why the European Union is planning on making all cars electrical by either 2024 or 2026.
Very good. Then. So, which means simple harmonic motion is actually practiced in various fields.
Yes.
Both in engineering and geography, and even at home we practice simple harmonic.
Yes, sir.
The body itself brings itself, shuts down wherever it's stressed, which means everybody comes to an harmonic solution. Thank you.
Thank you so much, Master. Okay.
You're explaining simple harmonic motion. I think we should have started with the diagram to carry everybody along. Because everything you are just saying is after to just talking. It's not that. This is what you should have started with. So next time, if you want to start a presentation, start with something that grabs everybody's attention. because it's going to have marks to the education. You don't just come and call, you just make just keep talking and talking and talking and talking. Fine, use the equation to explain most of what you're saying, but you should also start with the diagram. You start with the diagram, let us see where the sin theta or the omega or whatever comes into play. Do you understand?
And I'm going to be sincere, I really love the pronunciation of words. You pronounce words very correctly. Okay? I really thank you for that. And I think I'm going to suggest that attitudes should be one of the criteria for this, for this kind of session. Attitudes. Basically, when the sectors are being corrected, what kind of attitude do they put up because of correcting them? That will be one of the criteria the next time we have this.
Thank you so much, Master Morayo. Next on our list, we have Master Caleb Okere.
Good morning, facilitators. My name is Caleb Okere, and I'm here to talk about fluids at rest and motion. We'll go to the three topics that relate these things together. Number one being surface tension, number two being capillarity, and number three being viscosity. Let's start with surface tension. Surface tension is the force that acts on a body of water which makes it act like this. You can see this anytime in I put my hand in water and forms a droplet. You can see this in pond skaters when they're on water. You can see this if we put a needle on a blotting paper on water. This blotting paper sinks, but the needle doesn't. Now, let's go on to the molecular explanation. You see this as a body of water. We have molecule A and molecule B. Molecule B has, both of them, has many attractive forces around them. There's a radius around them which attracts other water molecules towards them, and these molecules also attract towards them. So the drag between them causes a resultant which is zero. But these guys, there is not much water molecules above the surface, so the drag is only at the bottom. This causes the tension downwards and makes the water act like a skin. Some applications that you can see surface tension used in is, well, say an umbrella. An umbrella is coated with oil-based substances to, actually repel the water molecules that come against it. Now there are spaces in between these fibers. When water enters there, surface tension acts on. Now this causes a skin which prevents water from entering inside. But if you touch on that umbrella, water is all going to go down. You can see this also in washing anything. When we add detergent to water, and let's say there's a fabric that has oil or dirt on it, this detergent decreases the surface tension. This causes the force that pulls this dirt out from the clothing. Detergents can also be used to cause oil and fats-based substances to become soluble in water. Generally, detergents and soap just makes the wetness of the water more efficient, making it able to remove dirt away from clothes. You can also see this in paintbrushes. When we put it into water, once it comes out, the paintbrush is all together than it is in water and the hairs fade away. The surface tension acts on the hairs and glues them together. Now let's talk about capillarity. In capillarity, you can use, for instance, an experiment with tubes. If you insert a large tube and a small tube in water, these tubes, water comes up more in this than in this. But if you do the same thing with, let's say, mercury. Mercury's own is less than that of water, and even if you put a narrative, it doesn't even come up at all at some point. Capillarity is the tendency of liquids to rise and fall in a narrative. Capillarity is explained in two terms: adhesive and cohesive reactions. Cohesive reactions is the attraction between like substances, such as water and molecules, while adhesive is the attraction between unlike substances, such as water and gas. You can use water and mercury as an example again. If you put on gas, mercury dissolves together, while water and gas makes it wet, in wet gas. You can also see this for the same reason in tubes. The mercury forms a concave meniscus downwards, while that of water forms an upward meniscus. You can also add surface tension to the mix. Surface tension pulls this water upwards the tube, makes it go all the way up until the weight of the water balances that of the surface tension. That's when it stops. Now, let's move on to viscosity. Viscosity is the internal friction between layers of fluid in motion. Viscosity, you can see this in maybe if you pour water from a cup and pour oil from a cup, the oil falls down faster than the water. And also, if you put a ball inside the water, a cup in the water and a cup filled with kerosene or oil, the ball falls down faster in water than the oil. We can tell this terminal velocity. The downward force of the ball outmatches that of the upwards. But in the case of viscosity, this viscous force acts opposite to the direction of the downward force. Up. Now, the ball accelerates fast, but then at a point it reaches its maximum velocity. I can tell it it's constant velocity because its acceleration is reduced to zero. Now.
Thank you, Master Query Caleb. I've gotten what we need to get. So, over to the judges.
Caleb, I really enjoyed it. You're so calm and free. You're very, very sure that that is very important. So, commend you for that. Then, I just want to ask, give me one application of service
using umbrellas. There are surface, there's water in between the fibers of the umbrella, and there are also this water makes a surface tension skin around it. This causes water not to enter or pass through the fibers of the umbrella. But if you put your hand under the umbrella, you can break this surface tension. So I advise not to.
You said it when you explained. I just wanted you to say it. Thank you.
Okay. Hello.
I was thinking, man. Have you heard of surface energy before? Don't heard of surface energy. I wanted to ask you the difference between surface energy and surface tension. Okay. Let's do surface tension. All right, no problem.
Okay. Thank you so much. The next person on our list is Miss Adinola Adesanya.
about the particulate nature of matter. First of all, we have to define what matter is. And matter is anything that has mass and occupies a space. And also, all matter is made up of tiny particles called atoms. The kinetic theory of matter assumes that all matter is made up of tiny particles called atoms, which are in constant motion. And it assumes, because it's in constant motion, that it has kinetic energy. So the basis of the particulate nature of matter, that is Brownian motion, osmosis and diffusion. And osmosis, in 1827, a botanist named Robert Brown observed from a microscope grains of pollen seeds using the naked eye. Okay, and also Brownian motion is defined as the random, constant, and irregular motion of tiny particles. An experiment that can be observed to show Brownian motion is the smoke cell experiment. I'll draw that for you. Basically, it's this. These are the small particles. This is the filament. And this is the glass rod. Moving on, diffusion. Diffusion is the migration of molecules to fill an empty space due to the molecules' constant motion. Factors affecting diffusion, that is mass, temperature, state of matter, and density. Diffusion can be experimented by when you spray a perfume on one side of the room, from the other side of the room you can smell the perfume. And now osmosis. Osmosis is the separation of two substances of different concentrations through a semi-permeable membrane. So now we go to atomic structure. An atom is the smallest part of an element which can take part in a chemical reaction. And the atom is made up of three different kinds of particles, which is proton, neutron, and electron. The proton has a positively charged and has density, a relative mass of 1. And
Thank you so much. Okay.
Now I want to ask this question: why do atoms? Why do they want to move? Yes. Why are they not in their positions? Why do they want to move?
Let's say solids. Their atoms are closely connected to intermolecular forces. So for gas has non-negligible intermolecular forces. So the atoms are free to move about, which makes them have high kinetic energy.
So what also discuss that?
Thank you so much. Any other?
Your total displacement is actually 0. Because walking 2 is 5, walking against it is -5. So making it 0 displacement. Thank you.
Thank you so much. You can all give yourself a round of applause.
Are we staying here for?
Yeah, you can go for